A 140 km/h cricket ball sharply reversing direction off a bat. A passenger lurching forward as a bus slams its brakes. These two events follow the same three classical laws that govern every interaction between mass and force. Newton's first law establishes that motion is a default state. This block will sit still or drift through space forever unless an external force acts on it. The second law defines that change. Net force equals mass times acceleration. We map these interactions using a free body diagram. We isolate the object and draw every force acting on it. Weight pulls down, the surface pushes up with a normal force, and a lateral force pulls it forward. Summing these arrows provides the net force value, which is the specific input required to calculate how the object will actually accelerate. Take the example of an elevator. When you stand on a scale, it doesn't measure your mass. It measures the upward normal force the floor exerts on your feet. While the lift is still, your downward weight and that upward push are in balance. When the lift accelerates upward, the floor must push harder to move your mass. That normal force increases, which the scale records as a higher weight. This apparent weight is calculated by your mass multiplied by gravity plus the lift's acceleration. Newton's third law is often misunderstood. While it states that every action has an equal and opposite reaction, these paired forces do not cancel each other out to zero. Cancellation is impossible because the forces act on separate objects. As you walk, your foot pushes back on the earth. That's one force. The earth pushes forward on your foot. That's a second separate force. Because the reaction force acts exclusively on your body, it creates the net force necessary for you to move forward. On an inclined plane, the downward pull of gravity splits into two components. One part pulls the block into the slope, while the other part attempts to slide the block down the incline. This graph shows how friction responds. Before the block moves, static friction increases to match whatever force is pulling it. Once that limit is breached, the resistance drops to a constant value known as kinetic friction as the block slides. Let's test this logic. In this Atwood machine with two unequal masses, identify the specific forces acting only on the heavier block. When we isolate that block, we see only two vertical forces, the tension of the string pulling up and the weight of the mass pulling down. Identifying these specific components is how you translate physical observations into solvable equations. We use the same isolation process for circular motion, such as a car navigating a banked racetrack. Circular motion requires an inward net force, met by existing forces like the track's tilted normal force. This force splits. The vertical component balances the car's weight, while the horizontal points toward the center, supplying the mv²/r needed to complete the turn. The process remains consistent. Isolate the object, map the vector arrows, and set the sum equal to mass times acceleration. This chart summarizes the 5 core scenarios: the flat block, the accelerating lift, the banked curve, the inclined plane, and the vertical circle. These diagrams provide the data needed to calculate acceleration and energy, forming the bridge into the next phase: work, energy, and power.